I guess I found this phenomenon in that when I was back in the day, I didn't have like real-time automatic calculation.
You only just got it back in paper? You just got it back in paper?
So, I mean, I knew what the scores were, but the actual, like, do you have a 90% or 80% that's nothing. You didn't know, right? You had no idea what your score, right? You had a rough idea. But I see it with my oldest daughter as well, right? Now that they have no classroom or whatever, it's in real time, you know exactly what's, I don't know. There's pros and cons. It's just more things we see.
I see little difference. I like it.
Huh?
I like knowing what I'm
Yeah. I mean, usually information can be good, but we also know there are consequences of too much stimulation. Anyway, all right. Welcome everybody. We're ready to go. Hey. This is our penultimate class together, and that means we have 2 more assignments. One will be due on Tuesday, and the other one will be due on Wednesday night. Okay, so but for multiple reasons, you'll see that the one due on Wednesday night has just a couple of questions, and you should have the answers more or less. I mean, you'll have to do some calculations, but you should have it out there. I made some mistakes, to be honest, in session 25, and one of them is easily, correctable by changing the problem. The other one's a little more complicated to change. So you're just going to get a little bit condensed. This session has a lot of slides in it as well. We have a lot of material to cover, so I'm not quite sure if we're going to get through everything today. If we do not, then we'll cover it on Tuesday. Okay, and hopefully, I don't want to, oversell, but hopefully we'll also have some time on Tuesday to kind of look back at the course and think a little bit about where we've come and everything that we've hopefully learned. This has been interesting. This has been an interesting semester, and I thank you for participating in the course. Yes, it is required for your major, but yes, it's nice that you're here. Okay, so any questions, technically or administratively, about what we've been discussing in the class so far? Please make sure if you haven't polished up your labs that you get them in by Wednesday night as well. Yes?
Do you have any idea about when the second exam will be released?
One of the graders told me today. It's today. So so it should be very soon. Thank you for your patience. Any other questions? Okay, here we go. So today's topic is going to be a flashback to beams, but then we're going to go a couple more degrees of integration, essentially, okay, to be able to figure out what the deflection, what the profile of the displacement across the beam might be. This morning, as I was kind of preparing for today, I added a note. You may really want to look at Hibbler's book. I have quite a bit of information in here. I think chapter 12 in Hibbler's book is pretty solid. Well, the whole book is pretty solid. It's very solid, right? There is a lot of information, and it would probably not be bad to see more examples if you want to get a better grip on things here. So this is one case where I'll try to get across a lot of information. Nonetheless, reading and looking at more examples in a book is probably not a bad idea. Okay. So we're going to derive these equations for deflection, and we'll describe, and even before we describe the procedure, we'll go ahead and kind of show you how to do it, and then there are some suggestions on kind of the step-by-step technique for doing it. And after that, we'll talk about 2 ways of the engineer, as I like to put it. In other words, the likelihood in 5 years of you doing these calculations, unless you're doing a graduate degree or you're having a good time on a Saturday night, is low. Okay, so what you'll see is that there are tables out there on the internet to help us calculate the deflections across a beam, and there's finite element analysis again. So you have one more opportunity to do finite element analysis. We're actually not going to use pre-po-max for this example. We'll just use the solver in the calculus solver in FreeCAD. Okay, so yes, I do want you to use FreeCAD because that's what everybody has access to. Okay, so please go ahead and download it or download it in the EIT cluster now. Okay, so here we go. This slide is a review of the sign conventions for our diagrams that we draw when we are performing equilibrium calculations using the method of slices on beams. So, as a recollection, we have this, and I just want to make sure, okay, yeah, you can see what I can see. So, in this case, you've got this distributed force across it, and we would say that if it's going in the y direction, which is typically what we use for the vertical direction, upward, then we would say that it's positive. As you know by now, often this quantity is negative because you have loads coming downward with gravity, either because you're setting a mass on it and there's gravity acting, or just get the mass and the distributed force of the weight of the beam itself. Okay, but that is the convention. All right, and we know that this quantity has units of newtons per meter. When we talk about axial loading on a beam, which is not usually that interesting to us, but as you also know, it can be something that we take into account for combined loading, even as recent, I guess, as last night for that assignment. So when we have that, when we have axial loading, we take a slice, and then the open face will generally kind of put a X coming out of that face, and then the force coming out of that face would be positive. When we have the opportunity to take a slice and we look at the internal moment on that slice, we then follow the convention outlined by Hibbeler, where it will be counterclockwise if Z is coming out of the board, as you see here, or it will be clockwise if the Z is going into the board, as we have it here, and the left side has been covered up. Okay. And then the one that always trips me up, I don't know what the appropriate way, but anyway, the one that I have to think twice about, because the M one, I just think about smiley faces. Okay. I'm not the most smiley person, but I just think about smiley faces, and that's the convention I remember there. But the V, and because of my as I've said it multiple times, my PTSD, that's not PTSD, but because of my issues with the book I use, which is different than Hibbeler's book, this throws me for a loop every time. So the V going down, all right, if you have covered up the right side, and the V going up if you covered the left side. And again, this is just writing the same exact thing, and then putting a note that I am confused because Crandall, Dahl, and Lardner use a different convention. Okay, so this is review. Why are we reviewing it? Because we're going to be using this stuff again. Right? This is our 5th session on beams. So now, do we know, right? We've said this before, we know with bars how to calculate stress, strain, extension. Shafts, we know how to calculate stress, strain, shear strain of course, shear stress, and also the angle of rotation, okay? The angular displacement, if you will, across it. Trusses, we haven't really talked about displacement too much with trusses, thank goodness, okay? It's it's definitely doable, all right? What you have to think about is the extension of each of those members, and then compile it, and then you can figure out what the displacement will be at a part on the truss. We haven't really talked about displacement with pressure vessels. Not super relevant. We're more concerned about whether or not that pressure vessel is going to be able to handle the loads that it has. And so now it's time for us to discuss deflection on beams. And we ask ourselves, why do we care? Why do we care about deflection? Well, we might need to meet certain functional requirements. Okay, so usually the first one is, will it fail due to yielding? Okay, so I would say usually our priority is first to make sure that we've met our requirement for the yield strength of the material. Okay, whether that's through maximum shear stress, through maximum normal stress, through Moore criterion, through von Mises criterion, right? But that's the kind of the first thing to do. The next, okay, yes, I don't necessarily want this much deflection, or I'm designing it so it doesn't sag too much. Okay, that's kind of the next level. All right, and so another issue that can happen is with deflection and also with bending stress is that you could end up having cracks that end up propagating and lead to fracture. And then we might ask ourselves a question, could we go between deflection and stress? So in other words, right, if I have a structure and I'm able to measure the deflection of that structure, maybe it would also be nice, I mean, in your mind you have the idea that, oh, if that branch of the tree is sagging quite a bit, and if I pull on it a lot, I can break it, okay? So we have this intuitive idea. Nonetheless, we can back calculate, and just like you use strain gauges or we talk about using strain gauges, right, to calculate strain, and then potentially going back and looking at what the stress is in the system, we could do the same with looking at deflections of a beam, and then figure out what the internal stresses might be. And wouldn't we like to be able to calculate the spring constant? Okay, so what in the world am I talking about there? Well, at the very beginning of the class, well, maybe not the beginning, but pretty close to the beginning of the class, we talked about bars as springs. We've talked about shafts as springs, right? So we've been able to assign a spring or a spring constant, spring rate, whichever way you like to call it, to these different structures to kind of shortcut and know without doing all the equations every time, without using PL over EA every time, but just say, hey, look, I know that delta is equal to, I know that the force is equal to K delta, and I know that K is equal to EA over L, so I can kind of quickly calculate the extension that I might have. So that might be one reason to understand the deflection in a spring constant. There's another reason that can be useful, and that is in terms of vibration. So if I've talked to you about the washing machine, right? Does anyone know the story of the washing machine? No? Okay. So my question is, let me just say, okay, everyone knows what a washing machine is, maybe. Not your dishwasher, the washing machine for the clothes. Okay. And there is a rotating drum in that washing machine. Often vertical, sometimes horizontal. Okay. Have you ever stuck your hand in that drum? And if it's the vertical one, it has the tower in the middle. And have you ever stuck your hand in it and gone woo, 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 woo? Wishy-washy? No? Okay. Well, when you go home tonight or you go to your dorm, walk into the laundry room and feel how much that whole drum can move around. It can translate side to side. Okay, is this story at all familiar now? Now you remember I've talked about this, right, Jonathan? Yeah, okay. So what happens is that washing machine is designed so that it doesn't operate at its resonance. Okay? The resonance would be induced because you have a motor that's spinning. And that motor is not, I mean, as wonderful as the drum is, it's not going to be 110% balanced. Okay? So it's going to be just its center of rotation is going to be just a little bit off from the actual rotation you're putting it on, and so it's going to have an eccentric mass essentially flying around it, and it's going to be causing it to want to go laterally, side to side. The reason why it's all loose is because if you recall your second order differential equations in math, and when you take dynamic systems and controls, or you just take dynamics, what you'll see is that, or mechatronics, okay? What you'll see is that as you go up in frequency for a second order system, you hit the resonant peak, right? You're coming along. Remember, anyone remember this? Like loading blocks, maybe? You're going, you hit the resonance and everything goes bonkers, right? But then you have a very sharp decrease in the amplitude, okay, as you go to higher frequencies. So what they've done is they've purposely designed that system to have a very low resonant frequency. What's the resonant frequency? Well, usually we say something like the square root of k over m, and that's in radians per second. Okay, and you won't divide by 2 pi, and that will give you hertz. Okay, so what happens is you design your structure not to vibrate much, or you design your structure to have a very low resonance so that when vibration gets induced, then you have very low amplitude for vibration. Now, we have some aerospace engineers, and we have lots of people who like aerospace, even if you're not an aerospace engineer, which is fine. I don't have a degree in aerospace engineering, right? But I like aerospace engineers. So, if you're thinking about a structure that might experience vibration and might look a little like a beam, what would you say that structure might be for aerospace people? Huh? A wing! Yes, a wing, right? Okay, so someone has done a very careful job to make sure that the vortex shedding and the aeroelastic problem that you might have with wings and the vibration that's induced on them does not cause them to vibrate so wildly that they come off the plane. Okay? So, this is another situation where you can think of it, it's kind of like a beam, and if you take aerospace structures, you're going to come back and tell me, nah, you really oversimplified everything. Yes, I really oversimplified everything. That's true. But the basic idea is that there is a situation where you would like to know what the effective spring constant is of this beam, okay? And you would like to know you'd like to estimate what the resonant frequency of the beam is, okay? And make sure that the input with the air going over, the vibrating motors, everything else, right, is not going to excite that resonant mode. Okay, and so that your wings don't experience too much amplitude of vibration, they stay on. Okay, super simplified example, but nonetheless relevant to beams and their deflection. All right, was that a stretch? Maybe. Okay, but that's a lot of the things in this class have been building on each other. Okay, and then another kind of thing. Maybe you get into acoustics and you want to design tuning forks. I don't know, right? I hope some of you go off into diverse, I hope all of us get a chance to do diverse things. But there, you've got the fundamentals after today. Get it? Fundamental 3? Anyway. And any musicians? No. Okay, so, yes, right. So you've got the idea, right, that if I can figure out the deflection and I can figure out what the spring constant might be, then I could also think about, okay, what kind of sound does this make when I vibrate this? And I guess here, this is just a picture. Obviously, you don't want these bars the bar to bend, or you don't want it to fail, all right? But you also don't really want it to bend, and you don't want it to plastically deform, even more than that. I mean, it's going to bend. Right? There's nothing you can do, right? The thing is going to bend by some amount, right? But we don't want it to bend. We want to be, within some limits. Okay. So, this is not the Olympics, but it kind of looks like one of those balance beams, doesn't it? All right, but what is it really? It's a pin on this end, and it's a roller on this end. Okay, and so we could say that this is simply supported, and then we want to talk about what's happening on these ends. All right, so on the ends, there's going to be no constraint on displacement. There's going to be no constraint on rotation. Okay, and there's no restraining force. Okay, and the curvature can be 0 at the end. All right, we'll get into curvature in a little bit. All right, but that's what you have at the ends. So that would be here and here. If you have pin constraints at the ends, okay, so this is now where essentially it's just like this, but we cut the beam, all right, and they don't have any free ends. So here you can say that, okay, the displacement is constrained on either end, and there's no constraint on rotation, okay, and there's a restraining force. Okay, you see that? Those are the boundary conditions. Why are we talking about boundary conditions then? Well, remember we had to use boundary conditions when we were solving for the internal shear force and the internal bending moments. We're now going to have to use some boundary conditions to be able to solve for the displacement of the beam, right? So it's good to know. I mean, if I just put a beam in space, right, and I drop it, that's not really a statics problem for one, but I need to kind of know, okay, where is this being constrained in terms of the forces acting on it, and where is it constrained in terms of displacements, and where is it also constrained in terms of angular displacements. Okay, we're going to talk about that. Okay, and we'll also look at symmetries and internal boundary conditions that we could, internal symmetries that we can leverage as well. Okay, a fixed wall will have a constraint on displacement, so there's not a wall. This is the free end, right? This is the wall. Maybe I should, maybe that. So right, so these are right here. This is a free end. This is a pin constraint, and this is a wall, and this is a free end. And so, just a point, the one about curvature being 0, that might be a little bit less intuitive, but you can kind of see it here. There is some curvature here, right? But once we get to the end, you see how it's just straight? It's just straight off, okay? That is going to, and this essentially, it's just coming straight off. All right, it's not that the slope has gone to 0. Remember, there's displacement, there's slope, and there's curvature, right? So we could say x dot, if you will, or dx d, I'll get to it. There's v, which is displacement. There's dv dx as you go across, and there's going to be the second derivative of v with respect to x. Okay, we'll get into it. But I guess maybe this is not a bad time to say a couple things about that. What you can see here is, even on this end, you see that there is an angle here, right? I at least with the vertical, with the horizontal. Okay? This, and you see how there's also some displacement. Okay? That went down, right? So we usually use v to describe the displacement, and of course, in this case, the v would be negative. And we use theta to describe this angle. This angle, theta, we describe as being the derivative of the vertical displacement with respect to x. Can you see that? That is no more than just saying that's the rise over the run, right? So that's like some delta little v, and this is going to be some delta x there. Okay. So that's how we're going to describe slope. Okay. We're going to describe it in terms of theta, and we're going to describe it in terms of the dx. And here, okay, this is going to be kind of like our curvature, and I don't expect you to remember all this stuff, but when we were discussing our derivations for the flexure formula for the beams, we said that if the center of a circle that is carving out the curvature, okay, or the radius of curvature, right? When rho would be the radius of curvature. If it's above the beam, we said the curvature was positive. And if it was below the beam, then we said the point that is, the center of that circle. If it was below the beam, we said it would be negative. Okay? But here, we can almost see here that there's going to be some curvature, all right, in here. And this curvature, which would be kind of like this 1 over rho, that is going to be, so we'll call that curvature. Okay? That is going to go with the second derivative. Like that. Okay? So first derivative is theta, second derivative is curvature. And you see the curvature here, it's opening up just like you remember from your calculus, and so that's going to be, positive. That's positive curvature, and you would take two derivatives to get that. Two derivatives of what? Two derivatives of the displacement of the y versus the x. And in this case, y we don't use, we use v. Okay. So hopefully that's not too revolutionary or mind-blowing. Okay. We call the deflection along the longitudinal axis of this beam, we call that the elastic curve. And we typically think of that as being along the longitudinal axis. Remember, the longitudinal axis was, sometimes I would call it the neutral axis, but really Hibbeler's definition. So this is the beam, right? The longitudinal axis is going along it, but then at any kind of specified point on the longitudinal axis, Hibbeler will say that is the neutral axis, okay, coming this direction. And this is the longitudinal axis. I'll mix and match them, all right? And actually, there's different terminology, again, by different books. But the basic idea is that we're trying to trace out what the elastic curve is, and that is how the longitudinal axis is bent. Okay? And there's not going to be that much difference between the surfaces, but yes, they're going to have slightly different paths, because you have that rho and that rho minus y, right? Remember that kind of business to the top surface, and rho plus y, because they're going to carve out different radii. Anyway, so we can say something kind of also interesting. This is the smiley face we talked about. And that smiley face, right, is associated with a positive moment. Okay? So when the center O is above the beam, we have also m greater than 0. Okay? So now we're starting to correlate the deformation, the geometry, all right, and the internal bending moment. Right? And whenever you start making relationships between forces or stresses and moments with deformation, that goes back to, remember, our third pillar of constitutive relationships, constitutive equations. So we're going to work toward being able to figure out how to essentially couple the material properties with the internal loads and the external loads, of course, to be able to figure out how things are defined. So once again, if O is above, then that's going to be positive. If it's below, then it's going to be negative, and that's what you see here. Okay. So in this case, the O is below, and we're good. Okay. Now let's just think qualitatively about what's happening. with the curvature of a beam. Okay, qualitatively. So qualitatively meaning at least I want to know is M positive or negative in particular areas. And also think a little bit about the shear force. Okay, so this would be the shear force diagram across this beam using the conventions that we've had in the class. So remember and what is this magnitude of the jump? Remember that? What is, if I want to know if I'm going from this point to this point, what is that magnitude? Yes?
P.
It's P, right? And we're going, P is coming down, right? And as we're going left to right, and this is going to become even more important today, right? We have to know if we're going, we have to know if we're going left to right, okay, or we're going right to left. So that's that drop there, and then this is what the internal bending moment diagram would look like. The displacement, we can intuitively say is, if I step, anyone ever stepped on anything, right, that is supported with some type of flooring and beams on either side, this is what you would expect, right? Or if you step on a 2x4 and it's supported on either end by a block, you're going to expect this type of the deformation. And what's cool is that this is intuitive, but in the class we've kind of been developing this intuition as well, right? What's happening with the forces and the moments inside. So once again, yes, we have positive curvature. And this problem is very similar, right? In that we have a shear force internally, okay, as we're going across, and the bending moment is also very similar, right? But it peaks at this location of P, and we have also a positive curvature. Any questions on what we're doing here qualitatively? Right. No numbers, just thinking about how does the deformation go with or how does the elastic curve go with what we've kind of been describing previously. So what we would like is a relationship between the radius of curvature and the bending moment. And we've kind of done this. Okay, we've done this. This is, okay? The shear force, I've said this also before, it does contribute some to the deflection, but typically it's not a big deal. And remember, we've done this example with the pure shear and the double shear, where we said, hey, how short do you have to make the beam such that the shear stress gets close or half of the bending stress? In fact, I said specifically half of the bending stress. And why did I say half of the bending stress? Well, now we know. If we're caring about the maximum shear stress theory, right, for failure, we need to have an understanding that a bending stress or a normal stress, right, is going to be twice the shear stress that we get under uniaxial loading, right? This is more circle, uniaxial loading. What's the equivalent shear stress? 45-degree material element, and the shear stress is just the radius of that more circle, and that was sigma 1 divided by 2. Okay. We've done this a number of times now. Please remember that on the 17th. Okay. So we don't care too much about the shear force, but we do care about the bending moment, and we are going to describe a distance along the longitudinal axis, and we're going to describe the bending moment as M, and we're going to say that there's a V, which is a positive upward displacement, okay? And we'll go from there. So this is kind of familiar in terms of this radius of curvature. We talked about the strain and the radius before. Okay? when we did the derivations, but we kind of tossed it out. We said, you don't really need to think too much about that minus y over rho stuff. Okay. Well, it's coming back. So here, the underformed element has A, B, C, D, E, F in the beam, and the radius of curvature, well, it's essentially infinite, right? Because it has to be out space or whatever to be able to describe this radius. And if we kind of look at a piece, okay, so this where the longitudinal axis is going through it, and we thought about, remember this is going to represent the width of the piece, some distance away from delta x, or some distance away from the longitudinal axis, and initially it has the same length as delta x. So here we can say that, well, delta s is equal to delta x. And the deformed element will look something like, I don't know, the keystone of a arc, or, of an arc base bridge. Arch, an arch, okay, but upside down, okay, here. So now we say, okay, this element has undergone some deformation. If it's A and B, they're closer to each other. D and E are farther apart from each other, and the angle that we've carved out is delta theta. And we're going to have a rho that goes to the longitudinal axis. And then we're going to have some distance, okay, above the longitudinal axis that we're going to call y, and that's going to affect essentially the local curvature and the local radius at any of those locations. And of course, the longitudinal axis is going to be unchanged, not deformed. So, the bending moment in this case, we say is going to be positive. That's going to be a smiley face. And let's think about what's happening in a little bit more detail. Okay. So here we have D, E, F, and we did this already, right? This is back in, I don't know which session. It's a long time ago. All right. And we have the rho, we have the delta theta, we have the delta theta, okay, and we have our longitudinal axis, and then we have the beam, all right? So this is just review. I'm sorry I'm going quickly, all right? But this is getting us to the response that we said epsilon is equal to minus y over rho. Okay, we did this already. So what do we do? What do we do? What do we do? What do we do with this? We have this deformation epsilon. Okay, and this is not deformation, this is strain, this is the strain, right? And what we're saying is that this is the change in, say, a length above the neutral or longitudinal axis divided by its original length. Okay, that's what this is. And what is ds? Okay, well, ds, we can say, is going to be equal to the dx, all right? And dx, that's the original length of the element that we've selected. And it would be the arc length of the longitudinal axis over the width of that element. So we can say that that is rho times d theta, whatever this angle that we've kind of carved out at this point. And what is ds prime? Well, ds prime is going to then be this rho minus this little distance above the neutral axis or the longitudinal axis, and times that arc that is cut out, right? So that would be the arc length here. That's what ds prime is. Any questions on this? No? Okay. So now we've combined these things and we got epsilon is equal to minus y over rho. That's fine. Hooke's law. It's been a while, right? For loading in one direction. So we have sigma equals E epsilon, elastic modulus. There's an important constitutive relationship, right? That Hooke's law. The Fletcher formula. Sigma equals negative my over I. Right? You see where this is going? There's a sigma. All right, there's a moment that we know that's positive. Okay. We can combine them, and we get this 1 over rho equals m over ei. Okay. Now, curvature is 1 over rho. Flexural rigidity is sometimes what we talk ei. Okay. So you see this equation. If I increase m, then 1 over rho increases. Make sense? Okay? Right? And then you already saw that. M positive and more positive, then curvature goes up. Right? 1 over rho is the curvature. Okay. Or rho goes down. Right? The radius gets smaller. This EI is called flexural rigidity. Right? If I increase the thickness of the beam, and that means that, and it's rectangular, right? That means that I've H'd it. I've increased my H, right? And that was the I for rectangular cross section. Remember that was BH cubed over 12, right? That's integral of y squared dA. So if I increase, so both elastic modulus and I have essentially the ability to resist the, and I being the second moment of area. They both have the ability to resist the moment and result in less change in curvature. Okay. So now we're getting close to being able to actually come up with some displacement relationships, right? What is our end goal? This is nice, right? This is nice that we have now this ability to kind of think about a radius of curvature or just straight up curvature, rho. And kind of foreshadowing, let's just go back big time. You're like, what is he doing? Well, I'm being annoying. Remember this? Even back here. We said, or we scribbled in, hey, wait a second. 1 over rho is somehow proportional to the second derivative of displacement with respect to x. And then we have this dvx, dv dx term, and we have v. Well, if now I've got a relationship that says m over ei is equal to this term right here, and my goal is to get the displacement, what do? I've got this now. It's m over ei. This, let's say, is equal to m over ei. And there's, right? How do I go from this? How do I then figure out, if I've got the left side here, how do I figure out what v is? I heard it. Who's mumbling that? You said integrate twice, right? That's what you do. Okay? All right, so that's what we're going to, that was worth looking through, flashing back through all these, through, I don't know, what is it, 20 minutes. Okay? So, we are going to do that. Okay? We have relationship between curvature and stress. Great. Okay, if m is positive, then rho is above. Rho is generally large. Yes, yes, yes. Okay, these things are true. Okay, and we can use them to think about how things deflect. Okay, that's great. Come on. I just want to get about to the deflection. Here we go. In your calculus class, you probably had this relationship. And we're going to greatly simplify this. Okay, but this is the definition of curvature. We're going to say that now our 1 over rho is equal to m over ei. We can put that in on the left side. And we've got a small dv dx, usually. All right? You see where this is going? Well, if I have a small thing, and it's down here, and then I square it, it becomes even smaller. That's nice and convenient. Because if I say this is now very, very small, then that means that I just have 1 plus a very, very small thing, and that becomes kind of 1 in the denominator, and so I get exactly what we just wrote on the slide 20 minutes ago. That the 1 over rho was going to be somehow related to the second derivative of the displacement with respect to x. So I can rearrange and I can say m is equal to ei over, or ei times the second derivative of u with respect to x. Now, does this look like something that we know how to solve for? Yes, we absolutely know how to solve for m at this point in this class. Okay, we better. This is the internal moment. But do you remember that there were those other equations? There was that w equals dv dx, okay, and that m is equal to dm dx is equal to v. All right, do you remember these equations too? And remember how we said, hey, sometimes you want to think about just starting from a distributed force across the beam, right? And then once we've done that, then we can figure out what the v is, and then we can integrate the v, and we can figure out what the m is. And now we're saying that if we know what the m is, we can integrate it once they get the slope of the deformation, and if we integrate it again, we can get the deformation, v. How many integrals is that? If I want to go all the way from a distributed force now to v, how many integrals do I get to use? I'll say it again. W equals dv dx. V equals dm dx. M equals now ei, second derivative of v with respect to x. Second derivative of v with respect to x, I have to integrate to get the first derivative of v with respect to x. V, I had to integrate to get, or I had to integrate dv dx to get v. 4 integrals, okay? Who likes integrating polynomials? All right, good. So you get to do it. It's going to be fun. All right? So, look at that. V, the big V. Now, this is where people also get a little bit hung up. And that's not a big hang up. I don't know of a better way. Books use V, little v for displacement and big V for shear force. Okay? So just be clear. So v equals dm dx, right? So v is going to be the derivative of this thing right there. Okay, w equals dv dx, which means it's another derivative, right? And you got ei ei times the second derivative of v, little v with respect to x. And if e and I are constant, which they often are for our problems, constant cross section, constant material, and material elastic modulus, then we can write these. And these you definitely want to have on your sheet of notes. They're not that earth-shattering, okay? And there are some steps that may be wise to bypass. For example, if you're given a problem where you already know m, and you're asked to figure out the elastic curve, which means you want a relationship, right? You want to come up with an expression for the lowercase v. Don't do four integrals, right? You only need to do 2 integrals. Okay? Because you just have to integrate m twice, right? In order to, and multiply by 1 over ei to get v. Lowercase v. If you have to start all the way back with a distributed force, then yeah, you could do these intervals. Often though, we know that we know how to figure out m. Okay, we're pretty good at figuring out the at least for determinant systems. Okay, and on Tuesday we'll talk about indeterminate systems. But for determinate systems, we're pretty good at being able to figure out what m is. So even though we have these fun-looking equations that allow us to do 4 integrals, often it's a good idea to do 2 integrals to figure out what m is. And once you figure out what m is, then do 2 more integrals to figure out what p is. Or maybe you don't want to do 2 integrals to figure out m, right? You can go back to statics and just use method of slices and figure out what the m should be. Okay? I'll be less particular here. Usually less particular. In other words, I won't say use the differential integral relationships. Well, I could, right? Well, you have to use integral differential relationships. Now they're embedded in here. Okay? But you could get to m just by equilibrium if it's a determinant problem. Any questions? Do we see, any questions on significance? Like, why in the world are we doing this? I mean, I think we tried to discuss that, or I tried to highlight it at the beginning. Any questions on the significance of what we have here with these equations? Any thoughts on the limits? So what types of assumptions have we made here? And when does this stuff break down? When can we not use these relationships? Any ideas? And of course I want to, yes, Brennan?
I mean, this is a equation assumption that it's static system.
Yeah, so it's got to be static. That's a good point, yes. Any others? Any other ideas? Yes, go ahead.
Linear elastic.
Yeah, so we're talking linear elastic materials, good. Okay, any others? What do we say about dV dx? Little d, that is, the derivative of the displacement with respect to x. We were saying it was small. Okay, so that's going to come out again. That these are going to be for small displacements, small angles. Okay. If you have a rubbery beam and it displaces a huge amount and has a huge angle as it displaces, this is not the equation to use. Okay, and even if you put it in finite element, you're still going to be hoping that everything works out okay. So this is for many cases, but it does have its limits. Okay, so we've got all that description. All right, so here we're not even going to draw. Look, there's no drawing in here. This is just a chance to do the math. Okay, there's not a diagram. All right. Now you can think of what the diagram should look like, okay, right? Just look at the problem for a second and tell me, what do you think this beam is experiencing and what are its constraints? So there's the math. And we're going to figure out deformation without doing any, no free body diagrams yet. And nothing like that. But what is this? What is the external loading describing? What are the boundary conditions describing? And how would you draw this beam from the map? Yes?
Distributed load.
Okay, so distributed load, right, because it's minus W naught, so you got remember distributed load across the beam, and it's across the entire beam, right? Because W of X is equal to minus W naught. Good. Now, okay, so that tells me something. What about the beam? What are the constraints? What do I have? How's this beam externally being supported? Yes. Can you put your fingers up like that again in the green shirt? Yeah. All right. That's it. Right. It's got essentially a pin on one side and a roller, we could say, but really it's like a pin-pin configuration. Okay. So that is a simply supported beam, and we can go ahead and start messing around with this. Okay. If we have this equation, right, EI fourth derivative of v with respect to x equals w of x, right? We can go ahead and integrate it once we've substituted the minus there not. We integrate it, and these are indefinite intervals, okay? That means we integrate and we introduce a constant. What do we have to do to figure out what the constant will be? Well, sometimes we will we'll be able to apply a boundary condition kind of immediately, okay? And other times it might be a good idea to wait. Okay? So we take this equation, and we know that it's equal to v of x, right? And so what is v of the big V of 0? Well, it's been given to us, and this is it. W not L over 2. Okay, and if we had done the free body diagram and the external loading, and then we took a little bit of slight, remember how we did these things where even when we use the integral differential relationships, we would have to do external loading first, and then we go just a little bit to the right of the left side, and just a little bit to the right of the left side, and a little bit to the left of the right side to figure out what the internal shear force was. But that's already been given to us, and that's what that value is. Okay? So we can say, all right, that's the boundary condition, and then we can pop it in. So it's just going to be, C1 is just going to be that. What's next? Well, now we have this integral. And we've introduced another constant, C2. Okay, we took the integral, okay, of this expression right here. Okay? And we already know what C1 is, but it's just kind of dangling here. And we've now got EI second derivative of v with respect to x. And what do we know? We know that this expression right here, EI second derivative of v with respect to x, is equal to the moment, right, m. And once again, we can plug in our boundary condition. We know that m at x equals 0, right, this is all at x equals 0, is equal to 0. So what does that mean C2 will be? 0, right? It has to be. So we plug that in, and we get that C2 is just equal to 0. So now we do another integral. We've integrated this expression. C2 disappeared. C1 I've now plugged in, and now we have another constant, C3. And what do we see here? Well, we can see, okay, this is the derivative. We don't have a slope really given to us yet, okay, or at all. So we're going to keep going to the next integral. Okay, so if you don't have a boundary condition that you can just put in, go ahead to the next level. And now I've got displacement times EI and this integral, but I have two unknowns. How do I get rid of these unknowns? Or how do I solve for them? Yes, Prisha. Right, so probably easier to start with this one first, right? V of this little v of 0 is equal to 0. So that means that if I plug in 0, I get C4 equal to 0. All right. This one's a little more complicated. I had to plug in v of L, and I got to get 0 there, right? So I had to plug in L here, L there. And when I do that, we can solve for the C3. So C3 is this quantity there. And the result is an elastic curve described by this equation. And often what you'll see is we put 1 over EI in front of it. Okay, so we can say it looks like something like that. And we have this type of system, okay? And we've now got our expression, okay? And we could even figure out where the v is a minimum, and we can do that where x is equal to L over 2, and we can figure out that value, okay? All right, so Any questions? This one, any questions on this? Any thoughts, concerns? Okay. Some of them are moving kind of quickly, but you have a chance to run through this a little bit in more detail. So if you like integrating polynomials and plugging boundary conditions, this is the time. This is the moment. The moment, not the shear force. Well, it could be the shear force too. Okay. All right. So you have a question there, all right, that you get to work on. In this case, you're going to have the m of x given. So that's kind of nice, right? Because now you only have to do 2 integrals to get to the v, the little v. Okay. So we're going to talk about a procedure for solving for the lowercase v using these equations. First, think about it. Okay? Try to get a general idea about what the deformation looks like. I don't know if people are going to take pencils to this next exam and start putting their fingers and like doing distributed loads across it and then say, oh, hey, look, that's what it looks like, right? But that's the idea. Okay? So you want to get an idea of what the elastic curve will look like. Okay. This step can be confusing, and we haven't discussed it yet. We will now, though. Just like we would introduce these delta V's and these delta M's when you had a force applied, you know, a concentrated force applied, or you had a coupled moment applied to the beam as you're going across, we would then kind of say, ooh, I can kind of do everything up to that point, and then I got to change it up. Right? And then you go on. Or sometimes you go from the other side, okay, and that way you could, you know, you kind of do things, but you kind of like, oh, that point where there's another load being added externally, or another boundary condition you could even have, like an overhang, that was scary. It's still a little bit scary here. And so we're going to talk about how we break up the beam, right? It's like a relationship. You got this nice little beam, you got two towers on either side. They like each other, you know, with the beam in between, and then something comes in between them, and they're like, now you got a discontinuity, okay? It's like having kids. That's what happens. All right, so now we got to find the necessary expressions for moment, shear, and/or distributed loading. And we're going to integrate twice for moments, 3 times for shear, or 4 times for distributed loading. And we had to keep adding constants. So you already saw this, right? These are indefinite intervals. We have to keep putting constants in and keep solving for them. And as to solve for those constants, we're going to apply appropriate boundary and continuity conditions. And we'll get into continuity, what that means. Because right now we're just kind of looking at boundary conditions. But there are also some interesting things that happen when you are coming from far apart and you meet. Okay? And we'll talk, that's a continuity condition. And then we'll determine the expressions for the slope angle theta, and that we said is dv dx, and vertical displacement little. Okay, just like that. So now let's talk about breaking beams. Alright? And this is hard. Breakups are hard, right? In life as well. So here, right, if you just have the P at the end, everything's pretty happy. Okay, nothing too serious. But once you add this extra P, that adds nervousness to me. Okay, or maybe I get a little bit of anxiety. And in fact, on the last exam, initially I wrote it just with a nice distributed load across it, and then I said, well, what if we just make it so the distributed load goes halfway across the beam? And I started working it out. I was like, you all could do this, but in the limited time that you have, probably a bad idea. So just better to keep it with a distributed load across the top. And we see now we have this jump in the P, in the negative P, right, like that, and you can see that this is what you would get, all right? This is flat, so these are actually supposed to be lines with slope. Okay, they're not curves; they're lines with a point. All right, that's as bad as my drawing might be. Here are some options. So one option would be I'm going to describe two parameters, x1 and x2, and they both are with respect to the wall. This is an option. Okay. Another option, okay, because I'm kind of like, I want to describe what's happening here in between the wall and the first P, and I want to describe what's happening between the two P's. All right. Another option would be, okay, I'm going to describe what's happening with x1 up to the first P, and then I'm going to define another parameter, x2, from the second P, moving to the right. Okay. And then the third option would be, I'm going to describe an x1 coming from the left and an x2 coming from the right. So we've talked a little bit about this previously, okay? Like when we're using the integral differential relationships for calculating internal bending moments and internal shear forces, right? Sometimes we'll be like, well, it depends on which direction you're going, right? Yes, if you have a minus P, and you're coming from the left and you hit it, then you go down. But if you're coming from the right and you hit that minus P, then you go up, okay? Same curve results, but the direction you're going is going to change the direction that you're going to jump. So, when you're doing these types of things, again, keep in mind of the convention. I almost deleted this stuff because I was like, that's almost overkill, but it's a reminder, okay? That depending on as you're going across the beam, you gotta know which way your conventions are telling you to think when you slice. Okay. The big stuff though is this is the point on the left, is the left material is what we're trying to remember. Or it's been a little bit longer maybe since we talked about this. Okay. Now, when we break the beam into regions, we got to keep track of the sign conventions. Yes, okay, that's a given. We also need to keep track of slopes. Okay? And you can kind of begin to see this behavior. You see, if I'm going, now this has a positive curvature as well. Okay, yes it does. But you see, if I'm coming this direction from the left, that's positive theta. Okay? But if I come, and if I'm coming from the right and I go up like this, that's positive theta. You can see that? They are, though, actually, they would have negative, they'd have the opposite slope. So you see, if I'm coming from the left and I'm going down like this, then the slope is negative with respect to the x on this side, right? And if I'm coming from the right with this little x and I'm coming down, then the slope would be negative for this parameter on the right. Can everyone see that? It's the same idea I just discussed when you hit a jump, right? If you're coming from the right and the P was down, then you go up. If you're coming from the left and you go down, right? Then you go down. Okay? So the slope can be a little bit tricky. So here, displacement. All right. You see, I'm now writing this in terms of x1 and x2. So v1 would be associated with x1, and theta 1 would be associated with x1, whereas v2 would be associated with x2, and theta 2 would be associated with that x2. So here, right, they're going the same direction, they're going with the flows, and we can say that at this distance d, okay, this is where we talk about continuity. Right? So before we were talking about boundary conditions, which are typically on the ends, and you can have them in the middle too, right? But now we're talking about continuity between our different coordinate systems. So as we come down with maybe x1 and v1, right? And then we get to this location D, and we're going along with v2, and we get to this location D, we can say that the displacements, let's say here at the middle, or I kind of drawn at the middle, but D doesn't have to be in the middle, they're going to be the same. They're going to be the same. Okay? But if we come from opposite directions, okay, things get a little bit interesting. So you can see that they are going to meet up when the x1 is equal to d, and they're going to meet up when x2 is equal to L minus d. So they meet up, they shake hands, and they say, hey, what is our relationship to each other right now? Well, if we're V, the displacement, we say, oh, well, hey, you know, up is up and down is down, and you know, we're all equal on that. Okay? So you see that the V1 and the V2, they're equal to each other. But now we say, hey, okay, x1's coming and it's getting close to D, right? And it's got slope, and it's sloping downward. Okay, a little bit, right? It's sloping downward. And x2 is coming, all right? And it's also sloping downward. Okay? In this case, because we're coming from opposite directions, just like we said here, we had to introduce a negative sign. Okay? And it's right where they meet. Now, it turns out in the middle for this problem, okay, the slopes are actually going to be equal to 0. They're just going to, because it's going to bottom out right there, and so the derivative, the slope is equal to 0 there. Okay? But this is a little bit hard to kind of grip here, is that like if I start going up this guy, so like, you know, let's say that D is here, okay, at that location. Then I'm coming down here, right, to this location. I think I said it not so great before. Let's say the curve is like this, and now I meet over here. You see that as I'm going to the left, I'm going up, and as I'm coming from the right, I'm going up, and as I'm coming from the left, I'm going down. Those slopes have an opposite sign relative to each other. Okay, I hope that was more clarifying. Okay. So if the coordinate systems come from opposite directions, you have to introduce this negative sign to get continuity. Why is this important? Because, look, I can integrate and have indefinite integrals with constants that I don't know for, let's say, a V1 and a V2, right? And where there's some kind of interference being introduced, okay? Some force, something, some boundary condition, whatever it might be. And I can come to that location, and then I can try to figure out, okay, what's happening with my displacements, and what's happening with my slopes. Okay, and that allows you to then solve again for these indefinite, these constants that are in these indefinite intervals. Okay, so that's why we want to use, right? The previous slide I said you can apply boundary conditions and conditions of continuity, right? As we move across. Any questions on this? Okay, so the V's, the little V's, the displacements, those. Up is positive, down is negative. Doesn't really matter if I'm coming from left or right. The slopes, those do matter, and I need to match them up and put a negative sign, add an inverse sign. Okay. Yeah, I'm definitely going too slow. That's okay. The boundary conditions affect the, we'll just do the finite element on Monday. Okay. The boundary conditions, which means I have to delay that. Can't have it due because you haven't done it. Or I could have it due. Oh yeah, we have. So with the finite element will just be due on Wednesday. Okay. So the boundary conditions affect local parameters. Of course they do. Okay. Shear force, bending moment, vertical displacement, and slope. And you have rollers or pins. We know that the displacement is equal to 0, m is equal to 0. A fixed end, we have v equals 0, and theta is equal to dv dx is equal to 0. Okay, and the free end, and this is kind of what we said at the very beginning with better diagrams that were not mine, not my drawing, that we have a shear force of 0 and an m equals 0. Okay, okay, so let's just talk about this for a second. maybe these are probably pretty simple in terms of, okay, the displacement has to be 0 on top of a ruler or a pin. And at this point, you're happy whenever you see a ruler or pin because you know the moment pair is equal to 0. The force, you know, is an external force acting on the system you don't know. This one is maybe a little bit new. Not that one, this one. Okay? A cantilever beam at the wall, it comes straight out of the wall. Now, it can change right after it's left the wall, right? But that slope coming out of the wall is 0. So now, if you see a cantilever beam and you're doing these types of problems, you might be a little excited because you're like, ooh, I got one more boundary condition. I now know that the slope is equal to 0. Free end often is exciting too because the shear force and the bending moment are equal to 0. And you already knew that, okay, but this is just a reminder of that. But the displacement doesn't have to be equal to 0, okay? The curvature is equal to 0, but it could be going at a slope. So dv dx is not necessarily equal to 0 on a free end. Okay. Curvature, the second derivative with respect to x. Okay. So here's an expression or an opportunity, and you can go through this. I think it's okay. I'll try to also do some videos and stuff so it can explain how to do these prior problems. We're running out of time. This is not trivial stuff. It really isn't, so you want to take some time. And the problem at hand for this is also not trivial. It's actually a little bit, the first time I did it, I tried to take a shortcut. My shortcut was I tried to assume that the slope was 0 at L over 4. Okay, it turns out the slope is not 0 at L over 4. So it made me solve the problem faster, but it made me solve it incorrectly. What do we have to do? We have to use that continuity of the angle when we come from either side to be able to figure out what's going on at that location. All right. So and there's a solution for you, just in case you want it. Don't worry, it's on the slides, okay? And that's the solution too. All right. So it's really messy. All right. So we'll come back next time on that third part, the ways of the engineer, as we like to say. But let's go ahead and, oh, that's not the right one. We got it.